Dam safety in a changing climate is a critical concern due to the potential impacts of climate change on precipitation patterns, extreme weather events, and hydrological cycles. Here are some key aspects to consider. 1. Increased precipitation. Climate change can lead to changes in precipitation patterns, including more intense rainfall events and altered seasonal distribution. This can result in higher inflows into reservoirs, increasing the risk of dam overtopping and flooding. 2. Extreme weather events. Climate change is associated with an increase in the frequency and intensity of extreme weather events such as hurricanes, typhoons, and heavy storms. These events can pose significant challenges to dam safety, leading to concerns such as erosion, slope instability, and structural damage. 3. Changing hydrological conditions. Alterations in temperature and precipitation patterns can impact hydrological conditions, including river flows and sediment transport. Dams are designed based on historical hydrological data, but climate change may result in shifts in these patterns, requiring reassessment of dam safety measures. 4. Reservoir management. Climate change may affect the availability and distribution of water resources, influencing reservoir management strategies. Dams may need to adapt their operating rules to accommodate changes in inflow patterns, water demand, and environmental considerations. 5. Infrastructure aging. Many dams were constructed decades ago and may not have been designed to withstand the potential impacts of climate change. Aging infrastructure combined with changing environmental conditions increases the importance of regular inspections, maintenance, and retrofitting to ensure dam safety. 6. Risk assessment and adaptation. Climate change adaptation strategies for dam safety often involve comprehensive risk assessments to identify vulnerabilities and prioritize mitigation measures. This may include strengthening dam infrastructure, improving emergency preparedness, and incorporating climate projections into design standards. 7. Community resilience. In addition to physical infrastructure, ensuring the resilience of communities downstream of dams is essential for overall dam safety. This may involve implementing early warning systems, land use planning to minimize exposure to flood risks, and community education and engagement. Overall, addressing dam safety in a changing climate requires a holistic approach that integrates climate science, engineering expertise, risk management principles, and stakeholder engagement to safeguard both infrastructure and communities against emerging threats. In the next part of this video, you will learn dam safety in a changing climate, dam failure modes and some selected examples of catastrophic dam failures incidents that occurred in past and possible causes. Remember to subscribe, share and like this video.
An irrigation discussion problem we have here, it's mostly hydropower we are talking about. And hydropower is so great that it covers almost 100% of electricity production in Norway, but 45% in Sweden. So you can imagine that we really need these dams, and they also have to be safe. And of course, we have a debate here in Scandinavia about climate change, because climate change is going twice as fast up here as in global average. To run a hydropower system, you need a very complex system of reservoirs and dams, and you can see here just one example from one of the main hydropower producing rivers in Sweden. You see all these reservoirs, and you can imagine all the power plants, and you can also imagine how to design this. It's not a trivial thing to get the flood, see how it propagates from the up in the mountains down to the sea. Some dams are really big. This one is the highest dam in Sweden. It's about 125 meters, and the reservoir is almost 1 billion cubic meters. So it's a really big reservoir, and these reservoirs must be safe. But and we have made a lot of things to improve dam safety. We have had some incidents, and we also had rather spectacular dam failures in the 1980s that triggered a lot of the discussions here. But now we are discussing climate change. And if you look at this diagram, which I hope you can see, air temperatures are going up twice as fast in Sweden as compared to the global average. So the closer you get to the North Pole, the faster is climate change propagating. This means that we are really seeing the effects. It's coming slowly, but it's coming definitely. We can't stop it, and we see it very clearly now in our records, in particular in river flow, and in particular in the north. This we have a set of guidelines for design floods, and they are they've been around since the 1990s, but just recently we have added adaptation to climate change into the guidelines of design of our dams. And I will now go into, see if you can see this, just a second. Here is the guidelines, and the principle of the guidelines is, just a second here. I think I'm stuck.
We can see you. We can see the screen.
See the guidelines?
Yes.
I'm trying to carry on here, but I'm not managing really. Just a second. I can't continue with my presentation. Can you assist me?
You can't continue. So let me briefly bring that up on my end, and we'll present from my screen.
Yes.
No problem.
I'm sorry about this, but it's some technological thing going on. But I think I can do it without the presentation, if it's okay for you.
Let me just briefly. I think you could see it now. Yeah.
I don't see
Yes,
it.
then you can go ahead.
Okay. Normally, when you discuss then design and design floods, you talk about the worst possible precipitation, and you want to have a dam that can stand this situation. But when you come up to the north here, you have to also look into snow accumulation and snow melt. And as we have so big reservoirs, we also have to consider regulation, river regulation, and that is changing with the market for electricity. So there are also other factors that we have to discuss, and therefore we couldn't, when we developed the guidelines in Sweden, we could not use the classical probable maximum precipitation concept. We had to go further. We realized very soon that in order to get the worst possible condition for a complex river system with reservoirs, and as I showed you earlier, we need a full hydrological simulation. And that simulation was the foundation for the guidelines that were adopted many years ago. But that also means that when we come to discuss the impact of climate change on the reservoirs, we need to look at not only precipitation and temperature, we need to combine them. And we need to address the problem with going from a global climate change simulation to a local simulation for the specific river system. And therefore we have developed a quite complex modeling system at my institute, where I used to work at the Swedish Meteorological and Hydrological Institute, where we can downscale global climate model results dynamically. So we get the impact on both air temperature, which means snow accumulation, snow melt, and precipitation. And on top of that, we add reservoir operation simulations. So this is a quite complex system, and we have discussed that for a very long time between the power industry in Sweden and the authorities responsible for dam safety, and we have agreed upon a way of calculating this, and that is what I wanted to present, but I can't see that illustrations in on my screen here now. It's locked. Maybe you can see it. So the
Yes,
basic,
I think, yeah.
you can see it.
Yeah.
Yes. The basic principle is that we try to first analyze what is the most critical conditions for the system, and later on we say what will happen if we are changing climate, what will happen to precipitation and air temperature, and what will happen to the system in that case. And of course you can ask yourself, how do we know that? Well, what we can do is simply rely upon science. So we are using the latest available climate scenarios from the climate scientists, and this means that the target is moving a bit. But we are realizing that we have to accept that. We have to work with the moving target, but for the dams, it's anyway regulated that you should do it. You should analyze the possible consequences, but you must be ready to change your conclusions if science is developing. I think this is a new situation for, of course, for stakeholders, but it works, and it's all written down in our Swedish guidelines. And since 2022, the new guidelines are now in operation. So we are already looking at all our dams. There are thousands of dams in this country, in Sweden, and there are probably more in Norway, because they are producing twice as much hydropower in Norway as we are in Sweden. And now every time we go through a dam safety, make a dam safety assessment, we add the latest knowledge of climate change into the analysis, and we make simulations with a changing climate and also analyze this impact. This took some time to agree upon this, but we were able to do this because we had a joint committee consisting of power producers, but also authorities and scientists who are working and still working together and analyzing the latest results. This is maybe not possible in bigger countries, but in a small country like Sweden, we know each other quite well. So I think it was a very successful way of working, and that they have a joint committee, and all these actors are standing behind the guidelines. So that is why they're working quite well. But it's not only hydropower, because I don't know if you come to the last picture. Have you done that now, Jonathan?
Yes.
Picture of Stockholm. Can you see that?
Yes.
Have you been to Stockholm?
Not yet.
Not yet. If you look at that picture, you see Stockholm is by the water like most big cities. And in the far background, you have the Baltic Sea. It's just a small piece of it. And then you have this big lake in front of it. This is just one example where we have to do the same thing with community planning as we do with dams. Because the Stockholm city is vulnerable to climate change. If this lake outlet doesn't work any longer, we realized some years ago that we risked to flood the subway of Stockholm, for example. So the guidelines that were developed in the beginning to help the hydropower industry to build safe dams and to calculate the worst possible thing that can happen to a dam were later adopted to municipality planning all over Sweden. So it means that for hydropower, we also now have a safer Stockholm because the locks at the outlet of this lake, and they are doing exactly the same thing like we did for our high hazard dams for hydropower. I think this is a good illustration where a practical work between engineers, scientists, authorities is really useful, and I'm very happy that we have gone through this process together with a very, very open mind. With these words, I say thank you. I'm sorry that my presentation was stuck for me, but I hope you could get some impression about how we are working on this. So thank you so much.
Thank you so much, Sten. If anybody does have questions for Sten, either now or later, as a reminder, you can put those into the Q&A, and Sten will be sticking around for the Q&A, and we'll be happy to answer those questions then. Let's move on to the next part of our program today. Jonathan Lynch, who is the geotechnical lead here at Astera, is going to be presenting on the connection between earthen dams and climate change, and provide some global case studies as well. So without further ado, Jonathan, I will make you the presenter. The floor is yours.
Hopefully you can see that.
Yes.
The presenter through. Right, okay. Hi there. Right. Sorry, just fiddling around with this because out of my way. So yes, I just want to give you a brief overview of the geotechnical perspective of dams in general and climate change. I will be touching on some concrete dams, but primarily focusing on earthen dams. So climate change, how does it affect dams? What are the potential failure modes? A few examples, and I'll summarize that. It'll be very brief. I'm sure there's a lot more geotechnical principles that go into this, but let's just look at the ballpark figures. And on this particular image here, we've seen the Blackman Dam in Tasmania, Australia, showing some quite dramatic seepages about 2/3 of the way up the face of the dam. That was affected during the first filling of the dam. You can see there, first filling basically means when they were filling up the dam for the first time, and how quickly that took effect and how quickly seepage occurred. Quite clearly that accelerated into a piping event over in the far right side there. Luckily they managed to lower the reservoir level there and fix the problem. But given that this is happening on first phase filling, this is probably a construction issue, likely to be poor choice of materials or poor compaction or something of that matter. So really, why does climate change come into things with dams? Well, really, everyone's thinking immediately by an increase in rainfall. Sure, but like Sten says, there'll also be an increase in snow melt and glacial melt in some of the northern climates, and increasing runoff from the surrounding areas and catchment areas. Associated with that, we're going to have an increase in sedimentation from erosion. That erosion can flow into the dams itself, reducing its capacity. The higher water levels within the dams are also going to put loads on earth dams, possibly increasing in levels, such that there may be overtopping events, or putting more pressure on the structure and the foundation materials of a dam. So let's not pretend we do have climate change, although the COP28 and so on tell us so. What that means is we're likely to be having prolonged dry periods in summer, including droughts, and warmer, wetter winters throughout. The winters, we're going to expect periods of very high intense rainfall with short periods, but in places we're going to get longer duration, less intense rainfall. Again, meaning that ground is going to become saturated or near saturated. The sorry, I just was getting a message from the organizer there. So, and the drought can cause runoff as well. I don't know if you've seen some of the YouTube videos about showing dry soil, how dry soil can behave when you put an appended cup of water onto it. But again, it doesn't drain. There's less infiltration. The ground sort of slightly cements and it creates a crust. So there's going to be an increase in runoff. So the soils are going to lose their capacity to have that infiltration or absorb any water, and that increases the runoff. So a few of the dams failure modes that we generally know about, everyone probably realizes what they are: overtopping, the problems with foundations, in settlements, slope instability, and seepage. There are other failure modes which can impose loads onto dams, such as glacial melt, seismic activity, third-party, outside-party slope failures, material failures, of course. The Teton Dam in the United States, in this top right image, that was again another failure from filling. This one was actually a seepage event, which quickly accelerated into a mass piping event, and then catastrophic failure, as you can see, which is involved the deaths of 11 people and a lot of evacuation of people downstream from that. For any of you who have studied geotechnical engineering or dam engineering, you probably realize that this is an image on the bottom right of the Malpasset dam structure in France, near Nice. This was not an overtopping or a seep failure, obviously, but this was really down to poor engineering and poor geological judgment. The two opposing sides of the dam had slightly different strengths of rock, one with more foliation, and in fact there was a fault line running beneath the dam. During filling, several seepage or leakages were noted in the rock faces. The engineers didn't really think too much of it, and the filling continued. And at some point there was a catastrophic failure in the actual substrata, the geology, and there was uplift in the pore water pressures, caused a hydraulic uplift on the fault plane, and it actually ripped apart the dam, caused catastrophic failure and killing about 500 people further downstream. The dam had just been constructed. It cost about 500 million euros to actually construct this dam. That itself was lost, plus about 400 million euros in terms of damages. Many of these failure modes I've just talked about, though, can be exacerbated by climate change, in particular on earth dams. We should also talk about the critical age of dams, really, because a lot of the dams worldwide are fairly old. And if you look at the average age of large dams, we're looking at generally over 50 years. In the UK, most of our large dams are over 100 years old, which is quite frightening, also in Japan. And many other major countries there, at least 60 years old for the average age, including Sweden. So that means a lot of these dams historically were constructed before climate change was a thing. So certain of the hydrological surveys that were undertaken at the time of construction would have been based on information at that time, not allowing for an increase in infiltration and precipitation. And indeed, a lot of the dams were constructed before the principles of geotechnical engineering and soil mechanics were really well known and well understood. So things like material choices, quality control, placements of the foundation, etc., all come into play here, and we're now dealing with that historic relevance.
New experience.
So I mentioned overtopping, but before we get to overtopping, the spillways should come into play. If a dam increases in its capacity and its height, there is an emergency spillway which should release the water. But again, in terms of construction, if a dam is very old, like the Tobruk example in the top right with the photograph of the helicopter, Tobruk was constructed in about 1840. It's an earth dam. You can see there with a concrete apron on the spillway. And excuse me, during extremely heavy rainfall in 2019, the level raised so much that the spillway came into play. So the dam was relatively safe, except that the spillway was very poorly maintained. You can see the concrete panels there. They had vegetation growing between them. Some of the panels were uneven, such that the volume water flowing over the spillway then managed to seep underneath one of the panels, causing erosion and uplift, blowing one of the panels away, subsequently causing further erosion. And emergency measures had to quickly be brought into place. There was emergency pumping brought into place. The population downstream were evacuated. The RAF, as you can see, were called in to put in sandbags and prevent any further erosion. And also in the United States, the Oroville Dam here in California, again, spillway was brought into play. I'll just highlight here, this is the main spillway running down here, but there's an emergency spillway along the edge here. And initially, the main spillway was working appropriately until at such a point where the see the edge of erosion along the side there. The erosion started to happen, and again the concrete apron was disrupted and became eroded, and subsequently there was erosion underneath. At that point, they used the emergency spillway. Again, poor engineering here, because the emergency spillway was used. The erosion occurred pretty much immediately and started to creep back towards the dam face. So in this respect, again, another engineering flaw, another geological flaw, because the rock face here was treated underneath the major spillway has all been a very competent, very strong rock, whereas in this particular location, when the erosion has initiated, it's actually quite friable. But in engineering terms, they just treated the whole thing as one uniform mass. Most recent catastrophic event, unfortunately, was last year in September in Libya. We do know that this is associated with Storm Daniel, and reports are saying that Storm Daniel, again, is associated with climate change. Storm Daniel had made its way across the Mediterranean from Greece, where it wreaked havoc, onto the coast of Libya, in the north of Libya, where 400 millimeters of rainfall fell over 24 hours. Whereas normally they only get an annual rainfall of about 250 millimeters. We don't know, we haven't received the official report on this, but it's likely, extremely likely, that the dry soils there cause extreme runoff with that kind of rainfall, and the initial upper dam in the Wadi Derna overtopped. Don't know for sure, but Gnosis is probably that's what occurred, and then that flooded down the Wadi to the lower dam. And again, that lower dam was overwhelmed. It was already under pressure from the rising water. And then that flooded down into the town of Derna, causing several thousand deaths. The numbers are yet unknown, really, of numbers of deaths and numbers that are accounted for. Terrible disaster. This is an example, again, in the United States, the Fontaine Dam in Wyoming, constructed in 1965. This was subject to seepage initially, and then piping occurred quite dramatically. They managed to narrowly avert any severe disaster here by lowering the water level behind the reservoir. As you can see there, how the piping has developed. Right in the center of the image there, there's a large hole which traverses back beneath the dam, illustrating potential issues and what that could have actually gone on to cause. So it's still, again, this has caused a significant number of evacuees downstream, and the costs associated with all of that, as well as the costs of repairing this particular dam. More recently, again in the United States, the Edenville and Sanford dams, two earth dams. These were hydro dams. The Edenville dam is particularly large. It's about 16 meters in height and 2,000 meters in length. This was caused again by heavy precipitation and reservoir levels rising. At the time, the reservoir was coping with this. It has two spillway gates. One of them you can see here. They were both operational, they were both functioning, and seemingly being able to cope with what was going on. However, where the breach occurred here to the right,
to get to the speedway.
What was noticed there, and you can actually find this on YouTube videos, was a depression at the crest of the dam, signifying not overtopping, but signifying something wrong with the materials. And that actually quickly progressed. And if you can see the actual failure on YouTube, was very dramatic and very immediate. And the official report for this is suggesting that it's a static liquefaction problem, whereas loose sands contained within the actual earth dam structure itself became so saturated that they started to move apart, and then it bust the dam open, caused the breach, and in fact that whole dam flooded down into the valley below, hit the Sanford Dam, and overtopped that dam, caused significant amount of problems downstream. Repair costs in the region of $5 billion associated with this particular dog, and $200 million in terms of damages. I suppose really from an engineer's point was how do we know where that particular failure is going to occur? Where was the weak point in the first place? And again, any of you that studied engineering and geology and geotechnical works might know this particular site in Italy, Baijon Dam in Italy, which is a concrete arch dam, 262 meters in height, only about 250 meters across them. And this was holding back the river valley in an attempt to create water source and hydropower downstream. This in fact was not a dam failure. This was a geological failure of the landscape. If you can see the image on the right, a landslide occurred. You can see a slip plane here, and the material all was basically dumped into the reservoir itself, causing a displacement of the water that was in the dam itself. And a 200-meter high wave overtopped the dam, flooded down a very steep, narrow valley into the local town below, killing thousands down there. About 2,500 people died in that particular incident itself. But that again shows what can occur outside the dam structure itself. And this was due to heavy rainfalls again and filling the dam. But there was an existing failure plane, an existing weak surface, failure surface in that hillside. And in the filling of the dam, that the pore water pressures within the hillside were sort of balanced off by the height of the dam. As the dam was increasing in level and getting to dangerous levels, the engineers would reduce the level of water in the dam rather quickly, so much so that it caused an inequilibrium between the water in the reservoir and that was contained in the hillside. The pore water pressures increased so much so that the landslide occurred, creating this catastrophic incident in the hillsides of Italy. Other studies here in the UK, and this is related to highways, but it's related to highways earthwork assets, and in particular embankments. The Achilles Research Group recently in the UK have been doing a lot of work on infrastructure and earthwork infrastructure and its deterioration due to climate change. This is quite an interesting graph here showing the deterioration, or the number of expected failures of an earth embankment from present day up to the year 2080. You can see that the black dotted line here is showing the number of failures increasing from 100 up to about 150, and that's without the effects of climate change. When you run the climate change models, such as the worst case, the RCP 8.5, we're seeing annual failures accelerating, nearly doubling. So we could potentially expect 180 to 200 failures there. And when you focus in on the range of uncertainty associated with the climate change model, potentially we could be hitting over 200 failures by 2080 on earth embankments. Why is that important? Well, it's an earth embankment, so is a dam. Dam will be in the same situation, and we're potentially looking at more deterioration on the surface of earth dams, and that could weaken the dam itself. So just to sum up, the climate change impacts on dams is going to be an increase in in precipitation causing an increase in rainfall, reservoir heights, or potentially increase the loads on the dam structure. You might have an increase in seepages as a result of that. You need to look at the catchment area runoff because that's likely to increase, and there'll be a bit more sedimentation, a bit more sediments running into the dam, which means that they will fill a lot quicker than they used to. And the potential decrease in the resilience of the earthwork dam structure itself, all in all, such that we really need to start putting in. I know that there are monitoring situations in place for many dams worldwide, focusing on the dams themselves. I think we need to probably beef that up by looking at outside party slopes, the catchment area itself somehow, and then focusing itself on particular issues on the dam structure itself, such as seepages and so on. And with that, I'll hand over to Eddie.
And I wanted to start my brief part
Yes.
by reminding
Thank
us
you, Jonathan.
why
Eddie?
are we all here?
Pass you on
Okay,
as,
there's a warning by the
presenter.
United Nations that by 2050, most of us will live downstream of an aging large dam. Now, large dams were built a long time ago, and when climate change was not even in the lexicon. Nobody was talking about climate change. Now, how can we help in this area? Visual inspection is one of the most important parts of dams maintenance. It's predominantly visual, and people are doing it. So it's subjective. One person will see like this, one person will see a different thing, and when it's covered with vegetation or snow, it makes things more complicated. Some parts of the world you can see dams, you can see the surface of the dam only 5-6 months a year because the rest is covered with snow. We heard that Sam at the beginning of this afternoon of this webinar from Sweden. We have been to Sweden inspecting dams, and they are covered with snow. There's a lot of instrumentation, but the instrumentation is giving you data about where the instrument is installed. Whereas if you take a satellite image, for example, you will see the entire dam, and if it's a large dam, you better have a piece of software that will do the analysis and look at it in a more objective way. Now, trends is super important in monitoring dams, and it's better when you have all the data recorded in the same manner that it was acquired, so there are no differences in the sampling from time to time. And reports also can be done automatically if you have software behind it. A few words about where we started. Astera was founded in 2013, and the idea of using satellites or L-band satellite to look for water below surface was started in a project that the founder of the company did in the university. The first application that we sent to the market in 2015, by then the company was called Utilis, was leak detection of leakage from the distribution pipes in cities. As you can see, we give indications on one hand, the operator comes and pinpoints the location because there's nothing that you can see on the surface, and then the repair is carried out. Around 2018, we started expanding our activities into different markets. The company name was changed to Astera, and by today the company is providing solutions based on subsurface monitoring for water in several vertical markets. Now, what it's all about? An inspector goes to check the dam. He doesn't know what's going on underneath the surface. The surface sometimes is covered with vegetation, and he has to look for seepage, he has to look for piping, he has to look for possible landslides due to faulting. like Jonathan mentioned, and erosion, sinkholes, quite a challenge. And what we offer is to use satellite that penetrates the ground and can see below surface, and give you indications based on the technology. Now, we spoke about leak detection. Okay, the same technology, imagine that we use it to identify leakage below surface. On the surface you see nothing, but with the help of the radar that can see under pavement and several centimeters up to a meter, I would say here in this example, where the water is. So we can provide you indications in a geographic manner of where the problems are coming from. And this is kind of an aid to the visual inspection. Now, imagine that seepage is progressing through a dam, through an earth dam, at 50 centimeters per annum, enough that you see 1 meter below surface to get more than a year, 2 years, advance notice, so the inspector know where to look for, what to look for, and perhaps once the problem has been identified, do proactive maintenance and save lots of money. A few words about the technology. A radar mounted on a satellite that is looking to the Earth. A long wavelength has two main physical capabilities that we take advantage of: subsurface penetration and sensitivity to the dielectric properties of the target. Okay, so if we see water around rocks, soil, vegetation, snow, etc., that has a very low conductivity, water stands out, and this is how we can see that in the satellite image. Now you see here an example of how it works. Each pixel is converted into a soil moisture value, and we reprocess the soil moisture in order to identify saturated spots and actually send the inspectors, go here, don't waste your time in areas that are, according to the radar, less problematic. And in fact, if you look at the what we are showing, we are here offering you time. Instead of reacting once a phenomena appears on the surface, we give you a tool to find in advance where the problems may be coming from, and use common sense in order to at the end of the day, decisions are always made by the inspectors, by the people, and they are the ones to can use a new tool to look for where the problems are coming from. That's all I had to tell you about this afternoon. Thank you very much for your time.